talk about convex holes, and there's an algorithm for finding them, which is called gram scan. A set of points is convex, and usually we're talking about a set in a metric space, and usually it's the plane. And it means that if you take any 2 points in the set and draw a straight line between them, that line has to be entirely in the set. So the set K1 is convex. If I take any 2 points and draw a line, I stay within it. The set K2 is not convex because there's a point X, point Y here, and the line in between contains a point that is not in K2. Now, we're going to talk about the convex hole of a set. Now, again, all our examples will be in the plane, although we can talk about convex holes in the line or in three-dimensional space, or there are other examples. But we're going to say CH of S. Suppose S is the set of black points here. Then the convex hole of S is the smallest convex set that includes S. So if S is this particular set of 8 points, then this polygon here is then the convex hole of S. And what we'll notice is that if S is a finite set, the convex hole is always a polygon. Well, actually, it could be a line segment, but most of the time it's a polygon here. And our problem is that if somebody gives us n points in the plane, find the convex hole, which means find the vertices of the polygon. Now, we're going to do the Ronald Graham's algorithm for finding the convex hole of a finite set of points in the plane. The first step is to pick, well, this particular set has 11 points. The first step is to pick a pivot point, and it has to be a point that is definitely on the edge, a vertex of the convex hole. And one way to guarantee that is to pick the leftmost point, or the bottommost point, or the topmost point, or the rightmost point. If there are multiple points equally far to the left, then we have to pick the lowest one or the highest one, and so forth. So there is a unique point farthest to left here, and we're going to call that P for pivot. Now, the second step is to sort all the points except P. All the points have to be sorted in a certain order, and that's in the order of the slope of the line connecting P to that point. Now, in this case, the algebra is correct, meaning these slopes are monotone increasing if I go this way, but if I pick the bottommost points, the slope would go very high and then start at a negative high number and then down again. And you should be able to handle that. Alright, so I have these points labeled 1 through 10, and if you notice the line from any point to any other point is numbered based on that slope. So we think of an arm, if an arm here pivoting at the pivot would bump into these points in order. Now, one possibility is that there are 2 points on the same arm, and I don't have an example of that. I should have put that in. I'll tell you what I'll do. I'll put that in right here. I'll say there's another point here at the same exact on a line collinear with 0.5 and P. However, that point has the same slope here as the 1 to 5, and that means it can actually be completely ignored in the algorithm. So we delete those points from our consideration. So now we have 12 points, but I won't put a number here because it's deleted from the algorithm. Now, let's get started. what we do is we think of our arm as rotating and we build lines here. So I guess I'll use purple here. All right, so here we go, a line to number 1. Now, what we do is we think of a line being caught on this point and rotating it around. So we look at this number 2 and we draw a purple line there. Now this purple line is a possible edge of the polygon. Well, it turns out it will be, but we don't know that yet. And what we'll do is we'll draw this line. Now you can tell by eyeballing it that this line will not be an edge of the final polygon. But the algorithm, the computer that's following the algorithm doesn't know that yet. All right, now the next thing we go is we're doing the points in order, point 4, and we have an edge there. Now, what do? We observe that this is a reflex angle here. The angle at 1 and 2, those angles are acute angles. If we get a 180 or more degree angle here, then that point is eliminated from consideration. So what we do is we eliminate it and draw an edge here. Now I'm going to then pretend that this edge is erased by making it dotted. So this edge will no longer be in the algorithm, it will be deleted from the structure. Now one question that you have to ask is, what structure do we use? And the answer is a stack. The points that are deleted are always on the top of the stack. So every time we see a new point, we're going to push it on the stack. But before we push it on the stack, we see if it kills the top element of the stack. Maybe it'll kill the top 2 elements of the stack. All right, now let's look at this situation here. There. Now what do we notice? Again, a reflex angle going all the way around here, which means we have to kill this point, which means that these edges are no longer in the convex hull. And we draw a new edge here between 2 and 5. I'll get this right somehow. All right, now let's look at point number 6. If I go here, then I see the reflex angle, which means I'll pop 5. Now sometimes you pop 2 in a row. I'm not sure that happens in this example. I don't think so. So these are gone, and we have a new edge. So this is so far only the 3rd edge for the convex hull polygon. All right, so what happens here is, again, we do this, nothing. Again, we do this, nothing. But again, when we draw this line here, then we have to kill these 2 lines and put another edge here. All right, now when we go from 9 to 10, the same thing happens again. We kill these 2 lines and draw an edge here. Finally, that's the last one, so we then draw an edge directly back to P. So that means that our sequence, our polygon has, what, 6 vertices, P, point 1, point 2, point 6, point 7, and point 10. Now one question you might ask is, what is the time complexity of this algorithm? Well, it's O of n. Now, in this situation, how would we prove that? Well, every time we visit a node, we might, or vertex, we might kill a large number of other vertices. So you can't say that it takes constant time. Whenever we visit a new point, we might get a lot of extra time taking care of points that are already on the stack. But the total time is still no more than n, or O of n. So what happens is this. Each point gets 2 credits at the beginning. Now, credits are this imaginary kind of money from, I guess, science fiction stories. They're always using credits on some other planet. But what happens is every point is given 2 credits initially, and they spend these credits to do things. So, when you push, it costs 1 credit. And you pop, it costs 1 credit. All right, now, every vertex is pushed onto the stack once, but it has 1 credit to pay for that. Now, some of the points are popped off the stack, others aren't. But no point is popped off the stack more than once. So it has this extra credit to pay for its own execution, I guess, right? So you're born, you get $2, one to pay the obstetrician and the other to pay the executioner if you ever get there. And so the total number of credits is 2n, so it's O of n times.